Welcome to today's IBT ABC UTC Research Seminar. The presentation in these webinars highlight research work at the IBT UTC's partner universities. Each seminar consists of a 40-minute presentation followed by a 15-minute question and answer session. My name is Kathy Kroll. I'm the co-director of technology transfer at the IBT ABC UTC. I'll be moderating today's seminar. I'll be assisted by Don Diggeman, Georgia State Bridge Engineer, and Paul Lyles, the former Georgia State Bridge Engineer. Don and Paul will be moderating the question and answer session. We're pleased to welcome participants, approximately 600 registered sites for today's seminar. Our featured research project today is physics-informed machine learning for rapid damage assessment of reinforced concrete bridge columns. Our colleagues at University of Nevada, Reno will be presenting. But before we start the presentation, we'd like to thank our sponsor. The IBT ABC UTC is sponsored by the United States Department of Transportation through its University Transportation Center. The University Transportation Center's program has been in existence since 1987 with the mandate to help our nation's ever-growing need to maintain and enhance our transportation systems. The IBT ABC UTC at Florida International University and our partner universities are focused on accelerated bridge construction and innovative bridge technologies. We'd like to express our appreciation to the USDOT and their UTC program for supporting the IBT ABC UTC so that we can continue to serve the bridge engineering community. Two quick announcements. Please see the information on the screen for the World Bridge Engineering Conference. It's December 1st through the 2nd, 2026 in Miami, Florida. It will be a very valuable conference, so please put this on your 2026 calendar. There's a lot of really great information behind those QR codes, so please do download those or go to our website for more information. So our next monthly webinar will be on Thursday, November 20th from 1 to 2:15 Eastern. The presentation will be a one-sided approach, the longitudinal launch of Pretty Rock's Slide Bridge. This is a really amazing project. They longitudinally launched a 425-foot Warren Truss over a landslide area to reopen about half of Denali National Park's main road. It's just a really interesting presentation. Devin Altman with Jacobs will be doing the introduction, and he will be followed by Justin Sieg and Chris Sweekall from KWH Constructors. Registration is open. You can sign up now on the IBT ABC UTC website. Before I introduce our presenters, I'll review some housekeeping items. Many of you may know these webinars are recorded and posted on the IBT ABC UTC website in the section titled Research Seminar Archives. So you can access this and all previous seminars for future learning and to share with interested colleagues. We typically have a PDF version of the presentation posted for download, but we had some difficulty getting that transferred. So we will have that PDF version posted in the archives probably during this presentation. So if you need that, please go to the website to try to find it. The seminar today features the IBT ABC UTC's research project on physics-informed machine learning for rapid damage assessment of reinforced concrete bridge columns. This was conducted by our partner university at the University of Nevada, Reno. We're pleased to introduce our presenters, Parmita Ramani, PhD graduate student and research assistant, and Floriana Petrone, PhD associate professor, both from the School of Civil Engineering and Environmental Engineering at the University of Nevada, Reno.
All right, thank you, Kathy. Good morning or afternoon, everyone. My name is Floriana Petrone, and I'm an associate professor in the College of Engineering at the University of Nevada, Reno. For those who may not be familiar with UNR, we are a land-grant R1 research institution with about 24,000 students. UNR is also a partner institution of IBT ABC UTC Research Center, which has allowed us to collaborate closely with colleagues across the country country on innovative bridge engineering research and technology transfer initiatives. Within our Department of Civil and Environmental Engineering, our research spans a wide spectrum of fields, from large-scale experimental testing to advanced computational modeling, high-performance computing, and machine learning applications. So for all the students in the audience, if you are curious about research or thinking about pursuing graduate studies, please do not hesitate to reach out. We're always excited to welcome new students into our projects, whether your interests are in data analytics, experimental mechanics, or simulation-based engineering. Now, turning to today's presentation, over the past about 18 months, our team, especially Parmida, has been working on a project entitled Data-Driven Computational Framework for Rapid Post-Event Damage Assessment of Bridge Infrastructure Assets. The motivation behind this research comes from the growing need for rapid, reliable post-disaster evaluation of transportation infrastructure. Following major events such as an earthquake, transportation agencies need tools that can help them quickly assess which bridges are safe to use and which require immediate inspection or closure. So this project aims to provide a computational framework that can support those critical decisions using data-driven methods and physics-based modeling. So as you will hear from Parmida, a PhD student in my group, our approach combines traditional structural analysis techniques with modern computational tools to handle and interpret large data sets in an efficient way. In the first part, and I would say the core of her presentation, Parmida will demonstrate how she developed a computational tool to derive pushover curves and damage states for typical bridge columns. Then she will show how these algorithms are being incorporated into a larger automated framework for post-earthquake damage assessment, a system that is really designed to process large amounts of simulated and observed data to estimate bridge condition and prioritize inspection needs. With this, I'll stop here and hand it over to Parmida, who will walk you through our methods, results, and exciting next steps for this work. Thank you.
Good afternoon, or maybe good morning, and thank you for being here, everyone. My name is Parmida Rahmani, a PhD student in College of Engineering at the University of Nevada, Reno, working under the supervision of Dr. Floriana Petrone. Today, I'm going to focus on physics-informed machine learning for reinforced concrete bridge columns, especially predicting the lateral force drift response and the different damage states. This work is a part of a large framework we are building for post-earthquake bridge damage assessment. The long-term goal is a tool that can help bridge owners quickly screen many assets right after an earthquake. So here is the roadmap for today's talk. First, I will go and give you a short introduction and the explanation why post-earthquake bridge assets is such a challenging problem. Then I will walk through how we model bridge and generate a large library of nonlinear bridge simulation in OpenSys. After that, I will define the damage states that we use, and from there we move into the first core result, the predicting the lateral force drift response of a column and all damage states that we will see in a column. And then we extend that idea to a system level, predicting a full bridge dynamic response under the earthquake ground motions. Next, I will show how we extend and expanded ground motion dataset through simulation-aided data augmentation. And I will end it with conclusion and the next steps. So here, after a big earthquake, owners need a fast and defensible calls on which bridge stays open. And current tools are in two extremes: fragility curves, which are really fast but not that accurate, and a full nonlinear simulation that are accurate but far too slow. We also lack the near fault and large magnitude results. So training data miss the worst cases where it matters most for engineers. So our goal here is a physics-informed data-driven framework that both is quick and reliable. We built and validated 480 inventory-based bridge models with realistic detailing. We trained machine learning regressors to predict column force drift, shape, and the damage states almost instantly. We balanced our data set with combining the record motions with the synthetic one, and we expand and extend this work to a bridge level response. And finally, we deliver everything in a graphical user interface for a rapid regional screening. So before I continue, I just want a quick note that you will see the page number here at the bottom left corner of each slide. So if you would like to follow where we are in the presentation. And in this slide, I will show you the full pipeline and framework of our what we have done and what we are going to do. We first built and validate our 480 parametric finite element bridge models and define the damage state. We then augment the data by pairing each bridge with the recorded and synthetic ground motion to balance rare and near fault events. And next, we trained and tuned our machine learning regressor to predict the lateral force drift behavior and damage states, and also the final status of the bridge after an earthquake. Then we interpret the model with CHAP to see which bridge attributes drive predictions and check the regional robustness. Then we just optimize our input values that keeps accuracy high for the field use. And finally, all of this powers a graphical user interface for rapid post-earthquake screening at the regional scale. Now I will introduce the parametric bridge model that we use to generate the inventory. This is a reduced order finite element model that we can parameterize and replicate across many bridges. The goal is to create a large set of realistic bridge variants so we can study post-earthquake damage at a real scale. The bridge type we are modeling is a typical multi-span continuous concrete I-girder bridge with a straight alignment and seat-type abutment. And they are designed in what we called Era 2 after San Fernando earthquake and before the next major seismic code shift. So this is very representative of what agencies still have in service. Even though the today's focus will later shift to the column, the global model and the final goal includes all the critical components that influence our seismic response of a bridge. The abutment, the bearing, and the bends, and the foundation material. And this model is only a template that we vary to build our 480 bridge dataset. And in this slide shows how we represent the nonlinear behavior of each component in our bridge. And the idea here is that even though later I'm going to talk mostly about the column response and the column damage state, but in the global model, we don't just idealize everything else. We explicitly model bearing, abutment, shear keys, foundation, and using the component level nonlinear force deformation relationship for from the experimental literature and the Caltrans guideline. So here you can see the abutment backfill interaction, which is modeled using nonlinear passive and active spring following the Shamsabadi 2007 and Choi 2002. And we also include the pounding behavior between the superstructure and the abutment following Muthukumar 2003, so we can capture the impact and energy dissipation at the seat abutment. And we have the external and the exterior shear keys, which are modeled using the backbone curve from Megali et al. 2002, so they can resist the lateral load and then degrade. And the bearing pads are modeled using the backbone curves from Caltrans 2012 data, so we have a realistic flexibility and they are not just the pin supports. And the column and the bend caps are the nonlinear elements and nonlinear concrete and reinforcing steel soil material model. So the bridge model here is capturing all the main nonlinear mechanism that control the system level seismic responses, not just the column plastic hinge. And in this slide, I will zoom in on the column model because columns are where we define damage. And in earthquake and in past experimental studies, the most critical and visible bridge damage is usually concentrated in columns. Things like concrete crushing, buckling, shear cracking, or loss of the lateral load capacity. So after an event, an inspector typically classifying the bridge condition by looking at their column limited state. So in our framework, the column are the primary component that governs the damage state. We use the hinge ratio integration with 6 integration points so that the curvature demand is allowed to concentrate in the plastic hinge region rather than along the entire height of the column. At the base, we include 2 zero-length components in series with our column, a shear spring which can soften and degrade after the shear capacity is reached, a slip spring which represents bar slip and fixed end rotation due to strain penetration into the footing. And that means that our column model can represent both pressure controlled column and the shear critical columns, which are important in older inventories. And to capture the behavior of the column realistically, most and the part of the column is the elastic element, which is modeled with the effective cracked stiffness that keeps the model computationally efficient while still matching realistic global stiffness. And the plastic hinge length, which is assigned following Caltrans STC guideline. So it's scaled consistently with the column geometry and the bar properties. And for the section behavior inside the hinge zone, we use the fiber section, confined concrete, unconfined concrete, and reinforcing steel. The concrete fiber follows the confinement and unconfinement compression backbone after Chang and Manner, and the reinforcing steel fiber follows the cyclic stress strain with yielding, hardening, post-buckling degradation, which is consistent with the SDC and also the Zhang and Kunad model to capture the buckling as well in the steel. So here I will show you how we verified our column model. We compared our simulated column response against well-documented cyclic tests from the literature, which are available through the DesignSafe database. Along the bottom, you can see each plot shows experimental hysteresis in black and our model is in red. And what I want you to notice here is that the model is capturing the main seismic response feature that matters for damage assessment: the peak lateral strength, the post-yield strength degradation, and the pinching and a stiffness loss under the cyclic loading. That give us the confidence that the column formulation can reproduce realistic backbone behavior and cyclic degradation, which is important because our damage state are defined at the column level. The point here is that these tests spans different and detailing level, aspect ratio, and match the range we can see in our bridge inventory that we use that for our modeling. For example, you can see the longitudinal reinforcement ratio here, which ranging from 1.36 to 3.85%. And this shows us that our column model can be used for a wide range of the variety of the different properties of column. So going forward, when I'm talking about the predicting damage state, those damage states are grounded in column model that has been checked against the test data. So, and in this slide explains how we generate the bridge population used in our study. So our goal here is to build a statistically representative sets of bridge, not just one or two example model. So we start with the Caltrans inventory data for what we call era 2 bridges, and we extract the distribution for the key attributes like span length, deck width, column geometry, and the material strength. We then sampled these attributes using Latin hypercube sampling while enforcing the practical bounds from Caltrans that lets us cover the full realistic range of the parameters without just drifting into a combination that won't exist in the real world. And in total for this study, we generated 480 unique bridge models. This is a population we will later use for both our simulation and the machine learning, and we are planning to expand this number in future. And on the right, you can see that one example of how we sample. The span length is not sampled independently. It is conditioned on the number of spans. So a 2-span bridge and a 4-span bridge don't pull the span lengths from the same distribution. That preserves the real structural correlation, and instead of just pretending every variable is independent. So the takeaway from this slide is that the 480 bridge in our data set are not arbitrary. They are statistically consistent with the inventories, and that they are sampled in a way that they preserve the realistic geometric and detailing and what we see in the real world. After building the 480 bridge dataset, we also verified that sample bridge behave like a real bridge dynamically. What we are looking at here is the distribution of first 3 vibration period, T1, T2, and T3 from the eigenvalue analysis of all 480 bridges. Each histogram shows those modal periods vary across the population due to the difference in span length, column stiffness, and the deck mass. The dashed vertical line here represents a representative benchmark model, and the blue distribution is the overall population. And you can see that the benchmark lies inside the main density range for each mode. And that tells us that our sampling did not create structures that are unrealistically stiff or unrealistically flexible. So this step is basically a quality screen. It's confirmed that statistically the bridges in our data set have periods in the range we would expect for the multi-span, seat abutment, and the reinforced concrete bridges. You have heard me say that the columns control damage from past earthquake, and from inspection practice, most post-earthquake bridge decisions are driven by column condition, things like spalling, loss of the core, exposed steel, bar buckling, and so on. Because of that, in this work, we define damage state at the column level. We start from the qualitative descriptions in the Vousouri and Saidi 2010 and the related Caltrans style criteria, and then we translate those into a quantitative trigger points that we can detect in our simulation. Here is the damage state number 1 in light green, the minor spalling. You are seeing initial cover concrete spalling at the compression phase. Structurally, the cover concrete reached its crushing limit, but the core concrete and the longitudinal steel are still elastic. This corresponds to early visible damage, but not loss of the capacity. Damage state 2 is the major spalling. Spalling becomes extensive. The damage penetrates deeper, but the core confinement is still mostly intact and the hoops are still engaged. So you have a clear visible damage and you are consuming ductility, but you haven't lost any confinement cage yet. Damage state number 3 is the exposed core. And at this point, the cover concrete has peeled off enough that you are looking at the core concrete and reinforcement. This is the serious limit state because the confinement is now active and the local crushing of the core is starting. In our model, this mapped to a deeper concrete compression damage in the confined zone. And damage state number 4, longitudinal bar buckling. Here, the longitudinal reinforcement start to become unstable in compression and inside the plastic hinge region. In the model, this is where the steel material hits the buckling or strength degradation trigger. And practically, this is where inspectors start thinking about the restricted service or closure of the bridge. And the damage state number 5, the multiple bar buckling or rupture. And this is essentially the failure. And so these 5 states do 2 things for us. They align with what inspectors actually see and report in the field after an earthquake. And second, they give us a consistent numerical label and numerical values that we can train a predictive model on these data later. Instead of just using a simple binary label like the collapse and not collapse, we have 5 physical meaningful stages that give us much finer resolution. And it's important later because the machine learning model is trained to predict not just safe and unsafe, but which state the column is in. And from this point forward, when I am saying the damage state, I mean one of these 5 column level states. Now that we have defined the damage states physically, we apply them to every column in our bridge population. On the left, each gray line is the lateral force drift push curve from one column. The color point mark the first time that the column reach each damage state, from damage state number 1 in green through damage state number 5 in dark red. And you can see a very clear progression here. Damage state number 1 and 2 happen at slow drift, near first cracking and spalling, when the column is just starting to yield. Damage state number 3, which is the exposed core, tend to occur a little later around the post-yield area. Damage state 4 and 5, which involves bar buckling and rupture, show up in large drift softening range, where the column is losing its strength and stability. And on the right, we are looking at the drift ratio at first occurrence of each damage state across all columns in our data set. So for example, how much drift does it typically take for damage state number 1 to appear? What about 2, 3, and so on? And you will notice that the lower damage states have tighter, more concentrated distribution, and that's because the earliest falling tend to happen in a fairly repetitive and repeatable drift range. And as we move to damage state 4 and 5, the distribution gets broader and shift to a higher drift. That's where the details like confinement, axial load, and reinforcement ratios start to matter more. And the takeaway here is that we now have a consistent physics-based values for every column in our inventory. And those values and those labeled targets are exactly what we will ask the machine learning model to predict for us later. Both we want to predict the force drift response and each damage state for each column that we have. Here, these are the structural bridge column feature we use as input to train the machine learning model. Before training, we looked at the feature correlation among those input values, the concrete strength, steel yield strength, aspect ratio of the column, longitudinal reinforcement ratio, and transfer reinforcement ratio. What you are seeing here is a Pearson correlation matrix. Most of the off-diagonal values are close to 0, which means that these inputs are not strongly collinear in a linear sense. And that matters for two reasons. We are not just feeding the model a bunch of redundant copy of the same variables, and it let us interpret the model more clearly and cleanly later, because each feature is bringing different physical information. Now, it doesn't prove there are no nonlinear interaction, but it does confirm that we are starting with physically meaningful and distinct prediction. So now that we know that our inputs aren't just a repetitive information, we can ask which of these features actually control the force capacity and which controlling the drift values at each damage states. These plots ask a simple question: which structural feature matter most for the targets we want to predict? On the left, we are looking at the lateral force capacity at each damage state. Two trends are really clear here. The longitudinal reinforcement ratio is strongly positive correlated with the force. More longitudinal steel means higher lateral capacity, and it is exactly what we expect to see. The column aspect ratio tends to be negative, correlated with the force, and taller, more slender column can't push as much lateral force before they hit the same damage state. And on the right side, we are looking at the drift ratio at each damage state. Basically, how far the column can deform before it reaches damage state number 1, 2, 3, and so on. Here we see a different story. The aspect ratio shows a very strong correlation. It means that cylinder columns generally reach a given damage state at a higher drift, which makes sense. But beyond that, in this view, it's hard to clearly see the expected roles of confinement, bar buckling, bar quantity, and because the influence of aspect ratio tends to dominate the correlation. And in other words, the slenderness is so strong that it can mask the secondary physics. So to uncover these mechanisms, here we hold the aspect ratio within a narrow range. Basically, we fix the column slenderness, and then we recompute the correlation between each input feature and the drift at each damage states. And now you can really see the physics emerge. For example, at damage state number 2, which we define as a measure spalling, a steel yield strength become more important. The reinforcement strength is now controlling how far the column can go before that deeper spall happening. And at damage state number 3, which is the exposed core, transfer reinforcement ratio, basically confinement, dominates. And better confinement holds the core concrete and keeps the cage engaged longer. So you don't expose the core as early. That's a much classic confinement mechanism for reinforced concrete bridge columns. And by damage state number 5, the multiple bar buckling or rupture, bar behavior takes over. Both the Fy and the longitudinal reinforcement ratio are strongly correlated with the drift, where those severe damage states occur. That lines up with what the inspector worry about after an earthquake. That's where you talk about restricted service or even closure. So by controlling for the slenderness, we were able to spread and see the role of the concrete strength, yield strength, and confinement. And importantly, those roles line up with how practicing engineers are already think about the column's damage and how we define our damage. And the targets we are about to predict with the machine learning and the lateral force capacity and drift at each damage state are still governed by physical mechanism, and they are not just an arbitrary statistic data that we just feed our machine learning model with them. Now that we have defined the target, the push curve shape, and the drift at each damage state, we can train our model to predict them directly from the structural feature. We evaluate 11 regression models, including the linear, the tree ensemble, support vector machines, and the small neural network. These bar charts summarizing the test performance and across several matrices: absolute error, root mean square error, normalized error, and R square, and the concordance correlation coefficient. And two patterns stand here. First, the support vector regression with the RBF kernel consistently give us the lowest error. For example, it's at or near the minimum root mean square, and among the highest R square and CCC on the held out test set. Second, it does it without a large systematic bias, meaning that the prediction track both the magnitude and the trend of the true response. So based on this comparison, we select SVR as our primary predictor, and we used it and we tune it, the hyperparameter, with cross-validation, and lock the model for the rest of our analysis and for the using in the graphical user interface. Now I will show you that actually look like on the column model, a model that the model never saw during the training process. Here I'm showing you a 4-column from the test set. So these were not seen during the training. For each column, the solid gray curve is the true pushover envelope for nonlinear analysis, and the dashed black curve is the model's predicted piecewise approximation, and the shaded region between them is the error area or energy, and the colored marker here are the predicted damage states. And there are two key takeaways here. First, the model is capturing the overall lateral force drift shape. The area between the predicted curve and the true curve is small, which lines up with the low root mean square error and high R square you saw in the previous slide. And second, and more importantly, the model is placing the damage states close to where they actually occur in our nonlinear analysis result. Up to now, everything I have shown was at column level under lateral loading, and we use machine learning to predict each column's pushover curves and the drift at which it reached to its damage state. Now we extend that idea to a full bridge response under a real earthquake ground motion. And here, for example, the bridge here is the bridge we want to evaluate. Think of this as one of, for example, of 480 bridge configuration in our inventory. It has a non-geometry, material strength, and the reinforcement detail. On the right, so is the capacity space for the bridge column, the lateral force and the vertical axis, and lateral drift on the horizontal axis. And this is the force drift demand surface we have already taught the model to understand. And the dashed curve line, the dashed curved piecewise line here, and is the model's predicted pushover or capacity curve for that specific bridge. We are not running a new nonlinear analysis here. It just comes directly from our machine learning regressor. And now we start assigning the damage state, which using the trained regressor model. Damage state number 1, 2, 3, 4, and 5. Now we bring in the earthquake. For example, here, this is one ground motion record. It can be recorded motion, synthetic motion, and for every bridge in our population, we paired it with many motion like this. And under that shaking, this bridge will experience inelastic deformation. What we ultimately care about operationally is, did it just crack some cover or did it start buckling the rebars? That is the information that matters to a bridge owner right after an earthquake. And the black star here is the predicted earthquake demand for this bridge and ground motion pair. Instead of running a full nonlinear time history analysis, the model estimates where the earthquake will push this system on this capacity curve and which damage state is reached at that. That means after an earthquake, you can screen a bridge almost instantly. Bridge is probably around damage state 2, so it's still serviceable, or versus this bridge is at damage state 4 and send an inspector immediately. That's the core goal: post-event and post-earthquake decision support, fast, physically informed, and scalable at the regional level. Now we have talked about the bridge side of the problem a lot. We built a realistic inventory, we modeled the column in detail, we trained our model that can predict the push curve and the column damage state. Now we need the other half of the equation, the earthquake demand. For the dynamic part, we use the recorded ground motion from PEER database. Now you're looking at the histogram of the spectral acceleration at 1 second at the fundamental and for both horizontal component. And you can see we have a ton of low to moderate intensity motion here, which is expected because most recorded earthquakes are not extreme. But once you get out and go into the higher spectral acceleration range, the really strong shaking that tends to drive bar buckling or column instability, they counts drop off really fast. And this is a problem. And those are high intensity motion are exactly where bridges are most likely to hit damage state 4 and 5. And those are the states where owners have to decide, do we shut this bridge down or can we use it? So to test how this affects predicted damage, we randomly paired the real ground motion with our 480 bridge model. And we did it twice independently, 2 different random assignments of bridge to the motion. And this bar chart shows the predicted probability of next damage state for those random pairing. There are 2 messages here. First, the consistency between the 2 runs tell us that the predictor isn't behaving randomly or biased toward a specific pairing. And so that it means that our model is stable. Second, you will notice that almost everything is living in damage state 2 and 3, and we almost never hit the damage state 4 and 5 or collapse. In this sample of recorded motion, and that's not because the bridge are magically unbeatable. It's because that our real ground motion, real recorded motion set underpresents the really damping and the high intensity shaking. And that is the gap. If we train only on these recorded motion and we use only this motion, the model doesn't see enough severe damage, and which are actually the ones that agencies care about most after an earthquake. So in the next step, we'll go to augment and try to balance the motion. We saw that the recorded ground motion don't give us enough really strong shaking, the kind that drives damage state 4 and 5 and the collapse. To cover that missing high intensity range, we use the simulated scenarios earthquake from PEER simulated motion database. This includes 50 scenarios, total 25 without concentrates high slip patch, 25 with high slip patch, and the multiple hypocenter location. Here is the San Francisco Bay region and the rupture scenarios. We vary the hypocenter location and the rupture slide to capture different directivity pattern. Basically different ways a real large event can hit the infrastructure. Now, this is one rupture type without a concentrated high slip patch, and this is with high slip patch. A high slip patch is where a lot of moment release in one zone very quick. That creates a strong pulse and very localized extreme shaking, the kind of demand that can push the columns into a bar buckling. And here is the special maps of the spectral acceleration at 1 second for the no high slip patches cases and with high slip patch cases. And so we cannot use all those synthetic motion because they will create again an unbalanced motions, because most of the motions are far from the sleep, far from the field, and they are not giving us that high intensity motion. So we start. I want to just somehow review and summary what we have done. We start with the recorded peer motions. Their spectral acceleration at 1 second distribution is heavy on the low to moderate intensity and thin in the high intensity tails. Next, we bring in simulation scenarios and filter them and keep only those cases that span the missing high intensity range. Then we merge the recorded and the filtered synthetic set to get a more balanced intensity measure distribution, filling the high spectral acceleration bins without overwhelming the data set. We pair this motion set with the bridge population and predict the most likely next damage state for each bridge and motion pair. We now see the damage state for and fire and collapse appear here. And although the distribution is still somewhat skewed toward 2 and 3 and collapse. To fix the remaining part, we train an initial model and interpret it. The feature importance shows that the pulse period and the spectral velocity are fundamental period of the bridge and several bridge attributes strongly driving the damage. And we use that insight to define a repeatable selection loop. Talk about it here. So in this slide, I'm going to show you a diagram, which is the control logic, how we iteratively build a balanced and physically consistent data set. We pick a primary intensity measure to organize the motion, starting with the spectral acceleration, and we compute that intensity measure for recorded motion and the parallel for the synthetic motion. Then we find the undersampled bins in the real motion distribution. Next, we filter our synthetic and simulated ground motion to somehow fill those gaps. We merge these motions together and resample to somehow flatten the intensity measure histogram. We paired each motion with our bridge inventory and ran a nonlinear analysis and get the label the most likely next damage states. And if the damage state distribution is still skewed and the variance is epsilon, we train and interpret a model to identifying a better intensity measure and key bridge attributes. Then we upload the intensity measure and go through the loop again. And we stop when the damage state spread meets the criteria, gives us a balanced training set that reflect the both moderate and severe damage. And this loop is why the final predictor generalizes. Coverage is balanced and the features are grounded in bridge physics. And imagine we are a California Department of Conservation. After an event, a user click a location on the map and retrieve the ground motion intensity measure for that site. And they select the bridge of their interest and enter its attributes, span length, number of column per bent, and so on. And our trained model combines those attributes with intensity measure and not only give the shape, the envelope of the cyclic push of the bridge, but also different damage state and the final states that the current state, the damage state that bridge will see and is in after an earthquake. And what we delivered here is a large scale data set of the generated and the 480 distinct bridges which are realistic, a robust ground motion selection, and train a regression machine learning model for piecewise pushover shape, continuous damage state matrices, and the earthquake demand. Our future work is that, for example, here in the California Department of Transportation or Conservation, you can see that the site number 1, site number 2, 3, 4, and 5 are the recorded and instrumented location. But if someone wants to see the bridge status after an earthquake in an uninstrumented location, so there's 2 paths for this uninstrumented sites. It can be, you can use physics-based simulation, which needs a lot of high performance computing and a lot of money and effort, or they can use the machine learning model and also use this synthetic motion to validate the machine learning model to use the neighboring intensity measure of the station and predict the intensity measure of the uninstrumented location and area. And thank you for your attention. And now we are ready for Q and answers.
My name is Paul Lyles, and I'm going to run the Q&A today. And we have some questions that came in before the presentation, and we'll go over those. And we have some that have come in during the presentation, and I think we'll get some more in a few minutes. So anyway, very, very interesting presentation. And the first question I have here, and these are pre-webinar questions, is how is the structural engineer supposed to feel comfortable trusting an AI rapid evaluation model? Then what is the legal liability?
All right, so this is a very good question, and I would say legitimate just question. And here, I want to start by saying that I will express my just own opinion on it. So in my view, legal responsibility will remain with the human decision maker and not the algorithm. And so in this regard, really these tools should be positioned more as decision support tools rather than decision-making tools. And so if we think about an adoption by agencies such that departments of transportation, this should be accompanied by standard operating procedures and documentation describing the model validations and, most important, the range of applicability. So really just in some sense, to some extent, the liability will shift toward misuse of the tool rather than the model itself. But I think, this also offers an interesting and a good perspective for us as, the developers, with the compelling need to include confidence levels in our predictions, really indicating what are the uncertainty bounds. Instead of like saying that this will be the damage with certainty, we will say that this is the prediction of the model with these uncertainties that will be affected by a number of factors we are aware of as developers of the model itself. So in a realistic scenario, after an earthquake, the Departments of Transportation, as we know, as Parmita was mentioning, will be faced with the pressing need to inspect hundreds of bridges. So these data-driven tools will help prioritize action, for example, for identifying structures, bridges in this case, that can be used for creating corridors. But this will not replace the final decision and responsibility of the operator, the engineer, to identify and verify that those bridges can be, for example, be opened right after the event.
Okay, we'll go on to the next question. And this one, it says, how do UHPC, ultra high performance concrete columns, perform in seismically active regions?
This question is outside of the current scope of the project. Our models target a reinforced concrete column, typically of the Caltrans Aero 2 inventory. Once the sufficient validated UHPC data exists, we can retrain the model and make it suitable for those bridges as well. But for now, it's out of the scope.
You said you had the Era 2 models is what you were using. That was 1971 to 1990. And UHPC came along after that. So, but I do want to point out that we had our January 16th, 2025 webinar that did involve UHPC columns. And people that are interested in this topic, they may want to go look up that webinar in the archive. So we'll go on to the question number 3. And it says, what is the maximum accelerated response spectrum that you would use in your model?
Okay, we balance the intensity using the spectral acceleration at the fundamental period and relative intensity measure into the high intensity tails, representative of a near fault scenarios from the semi-peer simulated data. to capture damage state 4, 5, and collapse. So we didn't extrapolate beyond the hazard consistent range. We didn't do anything. We only used the spectral acceleration. The last spectral acceleration value was available in peer simulation database.
Okay. I was wondering, you showed that map where you had the different earthquake curves on it, and around the state, you had the one that showed the picture. How fast can you get those curves, those acceleration curves?
Okay, our prediction is in millisecond because it's a machine learning tuned previously. So it just want to, in a millisecond, it will run it and give the push curve.
Okay. All right. Another interesting question involving AI. Can you discuss AI hallucinations in context with this project?
We constrain the input to the physics-based variables. We train within the domain. We apply the push curve checks and validate it with the experimental data and the surface uncertainties flags. So it's if a query, it's the pair is outside of that envelope, and the graphical user interface just pops up, note that the error and its value or the inputs that you give us is out of the scope.
Okay. And here's another one. It says, this is interesting research, but can it actually be used in the case of an earthquake? And then is there a factor of safety and also reliability?
We didn't do a factor of safety or reliability, but it's not it's just a hint, and it's just a flag that comes to the owners, and they can decide to send the inspector immediately, or maybe I can hand it to Dr. Petrona to explain more about this question.
Sure. So really, this is strictly related to what we were just describing about the reliability. And really, we haven't, and we're not going to introduce any safety factors. So we are just going to really provide possibly in the next future with our best prediction and with a range of just a confidence level. So with a range of uncertainty, making the end user conscious about some conditions where that prediction may be affected by a large uncertainty, and so where the inspection might still be, just needed, especially if you're talking about high damage, and cases where that uncertainty can be just very small, very narrow, and so meaning that we can have, larger confidence in those results. But I would say right now we don't have that, and we don't plan to have any just safety factor embedded in these prediction models.
Okay. The next question we have is, what data were used to train the model? Were all 480 representative OpenSeas model data used? And then what are the model inputs to reproduce it?
Okay, so we have 3 models. And first, for predicting the shape of the push curve, and it's using the column property. The F prime C, the Fy aspect ratio, longitudinal reinforcement ratio, and transfer reinforcement ratio. And also, these are the same inputs that we use for predicting each damage states. But for the final breach hold status after an earthquake, we use the combination of the intensity measure of the earthquake plus the properties of the bridge, the whole bridge, and the column properties, and the material properties, and so on. But the point is that until now, we didn't somehow optimize our intensity measure parameters yet. And we will do it for sure later to just summarize it to 4 or 5 intensity measure of the earthquake.
Okay. Did the training set include pictures of damaged concrete or just OpenSeas data?
It's only numerical data from OpenSeas, and we didn't use any image or visual and vision model.
Okay. Can this program be used in all concrete construction, and can we get all strength categories needed?
For sure, if framework, the idea of this work for sure can be used for other concrete or other structural type, it needs the data. It needs to use model the different structure and get the data. So yeah, the framework can be used.
Okay. The next question came in during the presentation. It says, is the condition of the bridge It's imperfections due to construction or issues on deterioration prior to the earthquake, included or simulated a real earthquake, somehow integrated in the models, since the bridges are not maybe necessarily in the original perfect condition?
No, we didn't consider that yet.
Okay, that's fine. We have a bunch of questions that have come in during the question and answers. I'm going to turn it over to Don Digamon, and he's going to pick up the questions. Don?
Thanks, Paul. Yeah, lots of questions came in, and let's get to it here. And it goes, this may be a different variation of that that last question, Paul. The question is, if a bridge got hit multiple earthquakes in the past, does this model consider the damages accumulated?
Yeah, so like the core idea here is that really just the capability of this model to just predict response is based on the data we use to train this model. So if at some point we're lucky enough to get data from these bridges, they may have gone through just problems with past earthquakes, with previous damage or deterioration, as you know, just in the last question, and then we're able to get this data on the response of these bridges, we will just need to retrain the model, so to use the same framework. So the same backbone of the methodology will remain the same. We will just need to retrain it with new data that we will be very lucky if we can do that. And then the model will be able to predict the response of those bridges as well.
Yeah, data is key, correct? And whether that data is accurate and complete.
Data-driven approach, yeah.
Correct. Next question, was there consideration for lap splices in the plastic hinge region? Was it included in the slip calculation?
So we are trying to make this model, we're using reduced order model, as realistic as possible, incorporating a number of phenomena that take place, we know, in real columns, including bond slip. And so in this model that Parmeet is using, she's incorporating bond slip, again, using parameters that come from the literature, from what has been observed, mainly in experimental data, but also from observations in the field. And so we do have the bond slip.
How long does it take for an owner to gather the data needed for input for a specific bridge? Some of the data seem to require an in-depth look at drawings.
No, to be honest, that the data is really obvious for each bridges, and I think the DOT have access to all of it.
I mean, we're assuming that they will just consult the structural drawings and get very key information on the materials, for example, steel yielding point and concrete peak strength, geometry, and in our, based on our preliminary results, in our view, there will be enough to obtain a response, prediction of the response for that same column and that same bridge.
All right, next question. It seems that SSI is neglected in the damage prediction. Therefore, the predicted damage state should be better validated from actual earthquake records and field observations. Any comments on that?
Yeah, so it's a good point. So we do have a simplified way to just represent the interaction between the foundation and the soil. But for sure, when it comes, for now, we have finalized the model prediction for the nonlinear response, lateral response of the columns. But then once we will move on, complete the analysis on the earthquakes, that's a great point. And we will try to retrieve as much real data from earthquakes as we can, yes, to address this just issue as well. And that will be kind of embedded in the data and the response of the bridge. And so it will be a key in that case to go back and look at the soil properties, the specific foundation, so that we link data in the correct way. But yeah, that's a good observation, and it's something we plan on doing.
Next question, some really great questions here. Is there a parameter in the model that considers the effect of post-event change in eccentricity of applied vertical loading on the substructure unit?
Okay, we don't have that because the model stops where we predict the response. And so if we're talking about unseating, so we have modeled the seating, and so the model itself will be able to tell if we dig into the model, but the machine learning, say, software-based, software, will not provide that information. For now, we're just really looking at the columns, linear response, but not at any just unseating or any linear response of other components.
This is maybe a little bit more programmatic question. Can you specifically explain the physics-informed aspect once more? Did you do that via only considering uncertainty in variables, or did you make any changes to the machine learning model itself, maybe in the training phase?
No, I didn't do anything in the training phase. It's just the data that we consider the physical behavior and physical side of the any variables and the combination of the variables and also combination of the earthquake and the bridges. Yes.
But introducing some physical laws is something we just will need to do for the earthquake part. So that will answer the physics based in a more rigorous way, the physics informed just machine learning. Again, that will come with the just more challenging part, which is the response under earthquakes.
Very good. Probably two more questions here. Considering the variability of materials F prime C and Fy, would it be more appropriate to obtain a prediction interval with a margin of error rather than a deterministic prediction?
Yes, exactly. It is, but we didn't talk about it today, but we consider a margin of the exactly of error for each of these damage state prediction for the shape of the curve that we predicted, MR top, upper bound, and lower bound, and also each drift ratio, and finally the final state of the bridge, that it does have a error area as well. And finally, by considering and combining all this error, we can give and tell the owners that this bridge percentage will be in this damage state, and this percentage will be in the next damage state. So at the final decision, it depends on the owner. But if it's damage state 2 or 3, so it may just consider that, okay, it's good to be open, but it's in 4 and 3, maybe they can consider to just send an inspector.
Okay, very good. And last question, and this came across, there was a lot of comments about great presentation, great research. So I want to say that as well before this final question. So where is the weakness in the data set to your knowledge, i.e. where should the industry be capturing different data sets to meet these shortcomings?
In my perspective, it's that yes, the data that all over the United States is really limited on the existing bridge. So some of the existing bridge data is not available in any data set, and some of the bridges are retrofit right now, but the data is not updated yet. So I can say that if they can spend more on updating the data and just providing the researcher with more accurate data, that for sure will be a better result and a better prediction for the final result of the bridge.
And if I can add also data from events, even small events, that will be so informative for us to really understand how real structure respond. We don't necessarily undergoing damage, but that will be helpful to just inform the model.
All right. Well, Floriana, Paramita, again, great presentation and information. Folks, that concludes our webinar for today. And please join us in January 2026, that's January 30th, for a research webinar, but also on the next webinar in November 2025. So thank you. That concludes our webinar.